Okay, so today it's the 12th week of our session, and what we'll discuss today is mostly antennas and radiation. And we would see how, if you have some antenna, what determines the capacity of power radiated, or what are the different characteristics that define how good your antenna is. So we would discuss about the parameters that are important for radiation with antennas. So that's about today's class, and we'll discuss some basic concepts. And most of these concepts are sufficient. If you understand the concepts, you can directly use those expressions to solve your problems. So we'd mostly concentrate on the concepts, and if you have some doubts, we'll try to clear them. So let us recall and look at how and why did the scalar and the vector potentials come into picture. So initially we know that there's an electric field, there's a magnetic field associated with an EM wave. But then we saw that it's often easier to deal with potentials. So mostly because, if you remember, for the electrostatic case, what did we say? We said that the electric field can be also written as minus grad of V, right? And then V is a scalar quantity. So dealing with V is much easier. And so once you find V, you can very easily find E using this relations. So in most of the cases, dealing with potentials are easier. And that's why we opted for defining our systems in terms of potentials. So just like in electrostatic case, we had this scalar potential V. Similarly, if you remember, because the divergence of B is zero, as you can see from the Maxwell's relations, and that tells us that you can write B as curl of A, where A is the vector potential. Okay, so that these things were things that we studied during electrostatics and magnetostatics, right? But now if you look at the general Maxwell's equations and try to use these relations and try to write the Maxwell's equations in terms of this potentials, you would see that that is very useful. And these expressions can give you the magnetic field or the electric field in terms of the potentials, the scalar and the vector potentials. So this is your Maxwell's equation, as you can see. And now what you do is, if you look at this Faraday's law expression, right? So curl of E is equal to minus del B del T. And now what we do is we try to replace B as curl of A. And that gives us that curl of E plus del A del T is equal to 0. Now we know that curl of gradient of a scalar is always 0, right? So that's why what you can say is that E plus del A del T can be some effective, the gradient of some effective scalar potential. That's what we are doing here, right? So this is just, you are taking this del A del T to the left hand side. And now this is interesting thing, that this tells us that this entire term E plus del A del T is now represented as a gradient of a scalar. Okay. So now what you can write is E can be written as minus grad V minus del A del T. And what do you see here? We see that now your electric field is represented in terms of your scalar potential and in terms of your vector potential. And if you are in the electrostatic case where your A is 0, del A del T is 0, so there, like, A is constant, so then you get back to the same expression as you got for electrostatics. So basically, why we are doing this? So first of all, we are doing this because the main point for us is that if you have some antenna, some source, okay, and then uh, there's a source and there's a receiver. And now what you want is, you want to see that if you have some dipole, okay, uh, some radiating sources, and from there what would be the electric field or what would be the magnetic field at some distance from this radiating source. That's what you want to find. And we know that if you can find, or if you can write your electric fields or magnetic fields in terms of scalar or vector potentials, your expressions might get simpler. So that's what we are doing here. We are trying to write the electric and the magnetic fields in terms of scalar and vector potential. So you can write B as curl of A. You can write E as minus grad V minus del A del T. Okay. Now you can use this relations in your Maxwell's equations. Okay. So suppose if you put this expression in one, that is the first Maxwell's equation, you get something like this. So this is an expression which replaces the Poisson's equation. Okay, so in the static case where there'll be no time dependence, you will get back the like del square V equal to minus rho by epsilon naught, which is your Poisson's equation. But this is the general case where you take into account the time varying effects. Okay, now you can also put the electric and the magnetic field expressions into the fourth equation here, right? And this is what you get. Now here you can also simplify this further, okay, using your vector algebra formulas, and you get something like this. So now here you can see that this part is similar to what we get for a wave equation, right? So del square A minus mu naught epsilon naught del square A del T square. This is like your wave equation, standard wave equation. But you have this additional term here, right? And that is equal to minus mu naught J. You would later see that if you can manage to simplify this term out, you would get back a similar expression as the wave equation. Okay, so that's where the gauge transformation comes in. So this is how you write your Maxwell's equations in terms of vector and scalar potentials. Now, here comes the gauge transformation. Why do you need to do the gauge transformation? Because see, this is a very complicated equation, right? So you want to simplify it. But while you simplify it, you want to make sure that your measurables, that is your physical quantity, which is your electric field or magnetic field, that should not get changed. But your potential, or like think of the case that, see, potential, you can add some quantity, some constant to a potential, right? Because physically what is interesting to us is the potential difference. And the potential difference is, or the changes in potential is related to electric field, which is of physical importance, right? So, but the absolute value of the potential is not very important. So similarly, the absolute expression for A is not important. What's important is the magnetic field or the field intensity that you get. So as long as you have the same electric field and the same magnetic field, you can make changes to your potentials in order to simplify your calculations. Okay, so that's what is this gauge transformation. So what you do is, suppose this is your vector potential A, and now you add some term to it, okay, alpha, and you get a new vector potential. Similarly, you get a new scalar potentials. But we know that for the magnetic field to remain same, the curl of these quantities should be equal. So curl of A prime should be equal to curl of A, right? And that is equal to magnetic field. So that tells you that curl of alpha should be equal to 0. So whatever you add here, the curl of that factor should be 0, right? And we know that gradient of any scalar, if we do a curl of it, that is always 0. So you can write alpha as gradient of some scalar lambda, right? So that means now you get a new, you can in principle write a new vector potential where you write it as A, which is your original potential, plus gradient of lambda, right? And when you take a curl, this goes away, so you get the same magnetic field. Now what happens to your electric field? The electric field should also remain constant, right? And we know that in electrostatic case, electric field is related to the potential as minus grad V, right? But if you take into account the time varying changes, then we also have to take into account that the curl of E is equal to minus del B del T, right? So in order to have the same electric field, what you need is the gradient of this scalar quantity beta plus this term here, the curl of, when you do a curl of E, you get minus del B del T, right? So that means del alpha del T. When you add this term, that should be equal to 0, right? If that is the case, then you get back the same electric field. And now you have just, you can write alpha again as the gradient of a scalar, and that's what you do. So you take this terms in common. So now you say that if you choose, sorry, if you choose some alpha and some beta such that this condition is satisfied, then you are good to go, right? So that is the freedom that your gauge transformations allow you to have. Okay, so you can write A prime as A plus del gradient of lambda. You can write V prime, which is some scalar potential, which is equal to V minus del lambda del T, right? These are your uh, these are the different ways in which you have the freedom of choosing your potentials. Now we'll talk about two very important uh, gauges, which is important and which makes things simpler for us, and that is what is useful, right? So we'll talk about the Coulomb gauge and we'll also talk about the Lorentz gauge. So in Coulomb gauge, what you do is you consider that you do so see you can choose your vector potentials such that the divergence of A is equal to 0. So if you do that, what do you get from this equation? If you go back, if you look at this equation, if you put the divergence of A to be 0, then you get back the Poisson's equation, right? So that's what you get here. And that makes your calculation of like calculation of scalar potentials very simple, right? This is something we have already done. So we know how to solve the Poisson's equation. And so that means if you choose this kind of gauge, you can easily find your scalar potential. But here, finding the vector potential is still difficult, right? You set the divergence to 0, but that doesn't simplify how you should simplify your calculations for finding A, right? So if you want to find A, you might have to use some other gauge, okay? And this is basically the equation that defines how your vector potential is changing. And as you can see here, it's not very simple to solve. Okay, so rather we choose another gauge, which is called the Lorentz gauge. And what do we do here? We put the divergence of A to be equal to minus mu naught epsilon naught del V del T. Now, how do we get that? So if you go back and see here, this is what you have got here, right? You see that this is your standard wave equation, but you had this extra term. But now if you choose your A such that, or choose your A and V such that this condition is like this term goes to 0, then you get back your simple wave equation. And that makes your calculations and your life simpler, right? So that's why what you do in Lorentz case is you take the condition that divergence of A is equal to minus mu naught epsilon naught del V del T, right? And if you do that, then you get this simplified expression. Right? This is similar to your wave equation. And again, if you use the similar relations, you'll see a similar equation for your scalar potential. So the virtue of Lorentz gauge is that here V and A, both of them are treated on equal footing. Okay. And it makes calculation of all the potentials easier. This operator here, del square minus mu naught epsilon naught del square del T square, is called the D'Alembert's operator. Okay, so in general, when you use the Lorentz gauge, these are how the potentials are related. Okay, so it's important to remember that whatever we are doing here is to simplify our calculations of finding the potentials, and that will again make things simpler in calculating the electric and magnetic fields. And that's what we actually want to find. Okay, we want to find the electric and the magnetic field. We want to find how the power is radiating from some radiating source. Okay, so that's the main aim here. So now we know how to use the different gauges. So now if you remember about your standard Poisson's equation, we know that this is how the potential is written, right? Del square V equal to minus rho by epsilon naught. And you can also write the vector potentials considering the Lorentz case as del square A minus mu naught J, right? And that gives you this simple forms. Here you don't have to consider the gauge. Here it's a simple static case, right? So this is something we have already got from electrostatics and magnetostatics. And you know that this is how you write the vector and the scalar potentials in the integral form. But now what happens when it's not static? So when things are changing with time, right? So in those cases, suppose if you have some radiating source and there are electromagnetic waves that are propagating, so you have some source, you have some receiver. Now, how do you quantify the amount of signal or amount of power that is reaching your receiver, right? So there, what you have to take into account is the fact that electromagnetic waves travel at the speed of light. So the signal that is reaching the receiver has started from the source some time ago, right? So that's why it's called that's why it's called retarded potentials. So the potentials that you're getting are at a time, so that corresponds to a time before, like the signal that reaches your source, your receiver is seeing the signal which has started from your source some time before. So that's why you get the retarded potentials. And what should be the time difference? So that should depend on the distance that the wave has to travel, right? So the speed of light is c, and if the distance that it has traveled is r, then we know that the time delay should be r by c, right? So in that case, tr, which is your retarded time, is given as t minus r by c. So this t minus r by c is the time where when the source, when the your signal has started at the source and you are seeing it at some time t. Okay. So now if you introduce this concept of retarded time in your potential expressions, you would get something like this. So here, this rho, or the current that is there in the integrals, that correspond to a time before your time of measurement. Okay. So tr is your retarded time that comes up in the expression. Okay. And r prime is your source coordinates, right? And this r here is the distance, or the space between the source and the field point. You are doing an integration over some volume over which your charges are distributed or the current is flowing. So this rho is the charge density that prevailed at point r prime at the retarded time tr. You are seeing the effect at r at some time t, which is later, which is after t prime, tr. Okay. So these are called retarded potentials, right? And this is just to say that, the light that we are seeing, that so it's the same thing, that when you're looking at the sky, you are actually looking at past, because the light that is, or engine, the light that is reaching us from a star has started from the star way before. Okay. So now, based on these concepts, we'll try to talk about this dipole antenna. Okay, so it's a source of radiation, and we will see how power radiates from a dipole antenna, and how does it depend as a function of position from the antenna. Okay, so it's a strong function of the distance from the antenna. You would see that there can be different regimes that can come up. So we'll discuss about that. So this is something similar, same as what was discussed in the classes as well. So here, if you have some current carrying wire, okay, and that has some very small length, delta z, which is much smaller than the distance from the field point. So if you are looking at the effect of this, uh, dipole antenna from far off distance, so when delta z is much smaller than r, so in that case, what you can say is, you remember here that you have this term, right? You have this integration of j over the volume, where j is your charge current density. So here, j r prime del v prime would essentially be just the current that is flowing along the z direction. So you consider that the current is flowing along z direction here. So it should be I into delta z, right? And then it's pointing in the z cap direction. So that's the direction of your current density. And your r prime is 0. So you consider that it's at the origin, right? Now you want to see the effect at some field point P. So first you need to find the value of A, or the vector potential at the point P. And how do you do that? So you know this is how the expression looks like, right? And here your r prime is actually 0, and you know that your A is along Z. So if the current is flowing along Z, so you can see here, right? So the direction of Z, direction of J would actually determine the direction of A. So because your J or the current is along the Z cap direction, your A or the potential should also be along the Z direction. But it's important to remember that when you talk about A being along Z, we are talking about the rectangular coordinate system, right? But when you have this dipole antenna and then you want to see how the effect is at some field point, it has to be considered in the spherical coordinate system, right? So where you take into account the effect from all the angles and all the entire solid angle that affects that has this effect at the point P. So now you want to find the potential components in terms of the spherical coordinate system. So you have to go from the rectangular coordinate system to the spherical coordinate system. Okay. So, but from the initial given condition, we know that the vector potential in the rectangular coordinate system is along Z. Okay. And if you look at, just by looking at it, you can think of the case that so the so here A is pointing along Z, right? So just by looking at it, it is telling you that there is no phi dependence, right? Phi tells you how your vector is oriented or how the components are in the xy plane. So if it is already in the z direction, that means it has no phi dependence. So a phi should be 0. When you go to the spherical coordinate system, your a phi should be 0. And then if you just think that here it makes an angle, some angle theta, that means the component in the radial direction should be az cos theta, and the component in the theta direction should be minus az sine theta, right? So now what you have to find is you have to find first the az, which is in your rectangular coordinate system, and then by using this relations you can go to the spherical coordinate system. Okay, so this is what you do here. It's just you are replacing the terms. Okay, so j dv is being replaced by I delta z. Okay, and it's only in the z cap, so you don't have to write explicitly z cap. And this is just solution. So here what you see is that you have e to the power minus j beta r, right? But this is not dependent on z, so you can take it out. And what's interesting here is that what is this exponential point? This exponential term is actually uh, signifying some phase change, right? There's some additional phase which comes up as the wave propagates. And if you write both the time dependence and the position dependence, you would see that it's actually considering the retarded current, right? So it's the current which has started at some point, and as it has traversed, so the effect of the current at some point, but as it has traversed, the wave has attained some new phase. And that is what is being given by this e to the power minus j beta r term, right? So you write I into e to the power minus j beta r as your retarded current. Okay, so in that case, this is how your az looks like. And then you can use this relations to find a theta and ar. Your a phi is 0. So now you know the components of your vector potential in the spherical coordinate system, right? We want to find E and H from that, right? A is not of importance. What we finally need is your field intensities. So now you use this relation that, so B is equal to curl of A, so H is equal to 1 by mu naught curl of A. And this is how you do, so this is just the expression for your curl. And if you do all the calculations, these are just calculations, so you get something like this. So here it's important to know that you have both 1 by r and 1 by r squared dependence, right? So if you take the magnitude of the phi component of h, this would go away, right? So its magnitude is just 1. So you would get 1 by r plus 1 by r squared dependence. And that tells us that depending on the distance from the dipole antenna, your field expressions would change. So different, so like at very small distances, you would see that it's just electric field. Okay, so these terms would all go away. While at longer distances, you will have 1 by r dependence. So all these things. Okay. So now, if you know your magnetic field, you can actually find your electric field by using this relations, or you can also use the relation which relates your potentials directly to the electric field. So any of it. So if you use these relations, you would get the radial and the theta component of your electric field. And even here you have 1 by r, 1 by r square, and 1 by r cube dependence. So what we would now look at is, we will look at the individual sections depending on how your r is. We would look at the different regimes. Okay. So in the far field regime, okay, so far field meaning what would happen here? So this is your expression, right? So in the far field regime, you would see that ER, so it has all the 1 by r square and 1 by r cube terms would go to 0, right? Because it's dying down very fast. So there your radial component goes to 0. Okay, so only the 1 by r terms remain. So this is your theta component. This remains, and then your magnetic field component also remains in the phi direction, right? It also has a 1 by r term. So only the 1 by r terms will remain. And here, now if you look at this, you see that both the electric and the magnetic fields has a 1 by r dependence, right? So if you find the Poynting vector magnitude, you would see that it would go as, it's given as half into real part of E cross H star, right? So the power density in that case would go as 1 by r square, right? Like the Poynting vector magnitude would go as 1 by r square. And now if you have to find the power, how the power is changing, so there you have to multiply by the surface area, right? If you do that, then it's 1 by r square into 4 pi r square. So the r square gets cancelled. So what you then get is a constant average power that gets radiated from the antenna. So at far from the antenna, this is how your power distribution looks like. It's a constant average power that you get. Okay. Now what happens when you are very close to your antenna? When you are very close to your antenna, your 1 by r square and 1 by r terms would go away, and what would dominate is the 1 by r cube term, right? So here you can see that your electric fields will have a 1 by r cube dependence, while your magnetic field does not have any 1 by r cube dependence, so it goes to 0. So it's negligible. So it's mostly, so it's approximately a electrostatic field that you experience near the, very close to your um, antenna. Okay. And there can be an intermediate region where 1 by r squared dominates. So in far field, 1 by r dominates. In near field, 1 by r cube dominates. But in the intermediate region, 1 by r square can dominate. Okay. So when will this case be? So if you look at this expression, this would happen when, so there's a competition between these two terms, right? So when, if you multiply by r below and above in this term, then beta r by r square plus 1 by r square. That's how we will get it, right? So for this term to dominate, your beta r should be comparable to 1. Only in that case, your 1 by r square term will dominate. And from here, you can see that r would be comparable to 1 by beta. And what is beta? Beta is actually a propagation constant, right? It's given as 2 pi by lambda. So that means your r would be approximately equal to lambda by 2 pi. And 2 pi is close to 6. So when r, that's the distance from the antenna, is approximately equal to lambda by 6, what you get is your 1 by r squared dominates, and it's more of an inductive field because here there is no radiation. It's not radiating power here. Okay. Now, in certain questions, you might be asked, so, when is the near field and when is the far field? So how far is far and how near is near? So in that case, you can use this relation. So anything smaller, when r is smaller than lambda by 6, you can consider it as the near field. Anything larger than that would be far field. Okay. Now, here the dimensions, like in the radiation field where you are far off, there the dimensions of the antenna can also tell you whether you can consider it to be a far field regime or not. So in that case, your r, which is the distance from the antenna, should in the far field regime should always be greater than 2 into d square by lambda, where d is your dimension of your antenna. Okay. And at the far field, if you want to find the average power, you would do something like this, right? This is what we were discussing. So so if you look at the far field expression, this is your uh, E theta and this is your H phi. So you find half of real part of E cross H star. Okay. And if you do that, and it should be in the radial direction, right? So you're doing a cross product between theta and phi. So it should be in the R direction, which is good because that means your power is being radiated in the radial direction. And if you use this relations, you would get something like this. So this is your average power radiation. Now, this is per unit area. So if you want to find the total power that is radiated from your antenna, then you do an integration over theta and phi. Okay, so that gives you the total power, and this is how the total power looks like. So this is important because this gives you how it depends on the dimensions, and specifically how it is dependent on how the dimension of your antenna is compared to your uh, wavelength of light. Okay, so beta has the wavelength involved. Beta is equal to 2 pi by lambda. So basically it's a delta z by lambda whole square dependence that comes up in the power. So that tells us how the dimensions of your antenna compared to the wavelength plays a role in cases of power in the power radiation. Okay. And what you can do is you can analogously define a radiation resistance where you treat your antenna as an effective resistor. Okay. So in that case, you can write the power as I square R subscript R. So this is called the radiation resistance. And if you compare from here, you can find the radiation resistances. Okay. Now there are this standard expressions for uh, radiation resistances depending on how the length or how the dimensions of your antenna is. Okay, so you can use these relations in your questions or while you are solving your problems. Now I would just discuss once yeah I would just discuss a simple question here. So here you have this magnetic field strength which is given. So your H phi is given. Okay, and you know that the field point is located at some theta, which is given as pi by 2. It's around 2 kilometers from the antenna. So your R is given. Okay. And the length of your antenna is given as lambda by 25. So it's given as a factor of the wavelength that is propagating, right? So this tells us that the distance at which we are looking is far way greater than the dimensions of your antenna. So you are in the far field regime, right? So then what you can do is you can use the relation for your far field magnetic field. And if you do that, this is how the expressions look like. So from here, you can actually find the current, right? That's what is being done here. So if you see, the current comes out to be some 0.5 A. Now, what does the question ask? The question says that these are the conditions that are given, but what is the power that is transmitted by the Hertzian dipole antenna at some length given as lambda by 2, at 2 kilometers, right? So now you know your current and you know that this is your length, right? So if you go back, you can see that this is how the relations are for a antenna of length given as lambda by, so when it's much smaller than lambda by 4 and you are in this regime. So then you can use this expression for your radiation resistance. Okay, so if you do that, you can use this relation to find how the power is transmitted. So similarly, if now you are said that it's a half wave dipole, so that means in that case you have to use the radiation resistance for an half wave dipole. So I think these were there is a book by these authors, and that's a very good book on antenna. That's what was recommended. But from there you can have a look how you can get the radiation resistance values. But these are very standard values which can be used for this kind of analysis. Okay, so in your questions, I guess there are similar questions where some you either there are questions which says whether you are in the far field or near field, where you can use this relation. Okay, try to see how r is compared to your wavelength and say whether you're in the far field or near field. Or if your expressions for, you might have to might have, like there might be questions where they have asked for finding the expression for your magnetic field intensity at different r. So there you have to use the relation of r accordingly. In the near field, there'll be no magnetic field, but depending on how the expression is, accordingly you have to use your expressions for the different fields. And you can also find the power and all other factors from here. So is this clear? If you have some doubts regarding this, you can ask me. Okay. So if there are no particular doubts, let's call it a day. And I hope in all these sessions you have learned something, like it might have, I hope it's of help. So yeah, that's it. Thank you. Message. Yeah, yeah, okay, okay. No, you don't have to be like for what exactly. Do you have any doubt? If not, then it's okay. And I hope this helps. Okay, okay, yeah. Cutoff frequency of a waveguide depends on characteristic impedance of the waveguide, the dielectric property of the medium of the waveguide, the dimensions of the waveguide, and the transverse and the axial components of the field. Okay. Okay. It does depend on the dielectric property, because you would have your, I think there's this velocity that is involved, right? So the wave velocity is a function of the dielectric medium. So that's why the dielectric property of the medium is a factor, and it does depend on the dimensions of the waveguide, right? So if you remember the expression of the cutoff frequency, suppose if you talk about TE waves, okay, then how will it be? It would be, in general, it's like um, C by, like there's a factor in front which is of for the wave velocity, and then there is a term, right, m by a whole square plus m by n by b whole square, something like this, right? Since m and n are present in the cutoff frequency formula, should 4 also be selected? The transverse and the axial components of the field. Uh, Not really, right? Because why do you think that the transverse and the axial components of the fields are important here? Because this is telling you for a particular uh, mode, okay, for a particular mode of of your vibration, like suppose for some mode of m and n. So what is m and n? That is telling you how your uh, uh, suppose if you consider TE modes, okay. So in that case, what is m and n? That is telling you how the modes are in the different dimensions, right? But that has nothing to do with what the transverse and the axial components of the fields are, right? It is just telling you what the periodicity should be. That sets the dimensions, sets the possible modes that could be there. So that, like, suppose how do I explain? Um, so see, if you write the formula mathematically, if you look at the formula, there is no ex, ey, hxhy terms in the expression for the frequency, right? What is setting up the frequency for the cutoff frequency? The cutoff frequency is set by the fact that you have some boundary conditions at the two surfaces of your waveguide, and that sets how your waves should be, right? So that gives a control over what wavelength or what modes are possible, but that doesn't set what your amplitude should be, right? Is it clear? Like, did I make sense? Because I don't have that slide here, so I'm not able to. But mathematically, if you think, then there is no component of field involved in the frequency expression, right? So it should not be the case. But even if you have to think of physically, the amplitude is not playing a role here. The magnitude of your ex or ey components is not playing a role here. What is playing a role is, depending on the boundary conditions at the two surface, you can have different modes of vibration. Okay, right. Okay, so any further doubt? Okay, so I guess that's it. Thank you. Okay, do you remember the transmission coefficient and transmittance formula? No, formula I don't remember. Uh, which transmittance are you talking about? The Fresnel coefficients or what exactly? Can you specify which expression are you talking about? Okay. Plane waves when discussing normal incidence. So it's like the Fresnel coefficients, right? Like n1 minus n2 by n1 plus n2. That would give you your reflection coefficient, and the transmission coefficient is something like 4 n1 n2 by n1 plus n2, something like that. Like you generally get different expressions for different theta, but normal incidence means theta equal to 0. So yeah, but yeah, tell me. There was a problem in assignment 7. Okay. Now I don't remember which problem exactly you are talking about. Can you tell me the problem? Let's unshare first. If you can share the problem with me, maybe. Yeah, yeah, sure. When a plane wave traveling in free space is incident normally on a medium having, okay, done it 4, the fraction of power transmitted into the medium is given by, okay, a plane wave traveling free space is medium. Okay, so you know the dielectric constant of the medium. So if you know the dielectric constant, you can tell about, so you can find the, I think it's simple, right? You can find the transmission coefficients. It's free space. So there you can consider the refractive index as 1. And then here you'll get the given solution was explained in terms of reflection coefficient. Okay. When a plane wave traveling in the free space is incident normally on a medium, traveling from one medium to another, the power transmitted into the medium Okay. It's, as far as I understand, it's about when I tried to solve using transmission coefficient, I did not get the same answer. Okay. When a plane wave traveling in free space, then it's incident normally on some media. Now a part of it would be reflected, part of it would be transmitted. Now it said that what should be the fraction of the transmitted light. Okay. So fraction of the transmitted power. Okay. So what do you do? Like if ER is your, it's given as 4, then the refractive index is root over of ER, right? Refractive index is 2. Now if refractive index is 2, that means um, what is the reflection coefficient? Reflection coefficient would be N1 minus N2 by N1 plus N2, right? So that is given as 2 minus 1 by 2 plus 1, that is 2 by 3. Okay, so if I take a square of it, you have to find the, so when you talk about power, it's intensity, right? So it's not amplitude. So you take a square. So what you get is 4 by 9. Hmm, am I doing it correctly or not? Not 4 by 9. It should be 1. Huh. Okay, okay. Now I understand. So you were saying that if you, so let me do the question. Okay, you're writing something, right? Okay, let me wait. Two eta 2 by eta 1 minus eta 2. That's the transmission coefficient, right? Now you have to take a square of it when you talk about power, because power is intensity. So it's 4. Transmittance equal to eta 1 by eta 2. Okay, transmission coefficient equal to eta 1 by eta 2. Okay, but I don't know about this last relation that you wrote. Basically, we know this, that the reflection plus transmission should be equal to 1. That should always hold, considering there is no absorption. So I don't think this formula is correct. Like eta 1 by eta 2 itself does not give us the transmittance. I don't know which relation. The last relation I don't think is what we use. This relation is given in the lecture, but I could not find it in the text. Okay. I don't know the context in which it might be written in the lecture, but generally the transmittance, whenever we talk about transmittance, it's not just N1 by N2. Okay. So it's It's always the same concept that you would have some rays, part of it will be reflected, part of it will be transmitted. So the sum of R plus T should always be equal to 1. Okay. Now, when you do this question, you when you do from the reflection part, then I think you will get the answer as 8 by 9, right? Yes, that is the given answer. Right, because how you are doing it is it's n1 minus n2 by n1 plus n2. That is your reflection coefficient. And then because it's power, so you have to do a square of it. Right? So it's 2 minus 1 by 2 plus 1. That is 1/3 whole square. That is 1/9. And then the sum of, so now r plus t should be 1. So that means it should be 8 by 9. Now, what you are saying is if you do directly from the transmission coefficient, you are not getting the same result. Is it the case? 2n2 by n1 plus n2. Okay, if this is the formula, then it should be 2 by 3. So, okay. Transmission coefficient is given as, okay, 1 second. n1 minus n2 by n1 plus n2. And you're sure it's n2 by n1 plus n2? Acha, okay, हाँ, I think so. Um, I'm worried. Is the formula correct? There should be a product, right? No? 2n2 by n1 plus n2. Then it's like 2 by 3. So 2 by 3 whole square comes out to be 4 by 9, which is not correct. Yeah. No, I think the formula is not correct. 2n2 by n1 plus n2. It's the standard Fresnel coefficients, right? Okay, let me. So the Fresnel coefficient expressions 2 n1 cos theta I by n1. Okay, n1 minus n2 by n1. So it should be 2 into 2, 4. Mhm. 1 second, there's some confusion happening here. I don't know, it's a 2n1 by n1 plus n2. Right. So when you go from one medium to another, so your n1 is 1. Your I1 plus 2 minus, okay, and this is 2 n1, that is 2 by 2 by 3, so it comes out to be 4. Uh, what's the exactly if you, that's the case, if you just do it by 1 minus reflection coefficient whole square, exactly. But then the formula comes, the value comes correct, right? You get the answer from there. But why don't you not get? There's some trivial mistakes that we are doing here because This is very standard. So if you just find the reflection coefficient, it is 1/3. So the transmission coefficient should be 2/3. Yes. This is 1/9. Oh, okay, okay. Now um, see the intensity summation should be equal to 1, right? Like R plus T should be equal to 1, where R is actually R, like the reflection coefficient square, not the other way around, because it's the intensity that is summing up, right? So when you talk about capital R plus capital T equal to 1, this is this is for the this is the reflected intensity and this is the transmitted intensity. So your last line is correct. So when you find the transmittance or the transmission uh, coefficient, that you are finding in terms of your intensity, and there you write it as 1 minus this. So that is fine. Why did I get confused with this? So you understand, right? Small r, just this ratios, they don't add up to 1. What adds up to 1 is the transmission coefficients, which is actually the ratio of intensities that has the square term. Then it will be fine. If we apply reflection coefficient is equal to eta 1 minus eta 2 by eta 1 plus eta 2 expression. Yes. So when you write reflection coefficient, it's eta 1 minus eta 2 by eta 1 plus eta 2. That you are writing just in terms of your amplitudes. Okay. Now when you take a square of it, that is actually giving you the ratio of intensities. So when you say that R plus T is equal to 1, that is actually the intensity. The intensity remains conserved. So that's why when you write transmission coefficient, it's 1 minus reflection coefficient whole square. We get the relation above that. Okay. So this is your reflection coefficient expression. 1 second. Small r is eta 1 minus eta 2 by eta 1 plus eta 2. Okay. Now you take a square of it, whole square, right? So it's n1 square plus n2 square minus 2 n1 n2 by n1 plus n2 whole square. So that is your capital R that you are getting. Now 1 minus that term will be equal to, yeah, see, you are getting confused in, wait. Let me, I think now I understand. It is like you have, like, we have got slightly confused. So see, suppose when you are writing, when you are just doing the amplitude study, then what do you write? You compare the amplitudes, okay? And from there you get some small r, okay? And this small r is written as Just follow what I'm saying and then see if it is making sense. Okay. So this small r is equal to n1 minus n2 by n1 plus n2. Okay. N is your refractive index. So small r is equal to n1 minus n2 by n1 plus n2. Now, this is your ratio of amplitudes. What you want to find from here is the ratio of intensities. Okay. So what do? You take a square of this term, right? And that is your capital R. Okay. So now try to take a square of this. What do you get? N1 square plus N2 square minus 2 N1 N2 by N1 plus N2 whole square, right? That is your capital R. Now capital R plus capital T is equal to 1. Okay. The sum of intensity should remain conserved, right? So now if you do that, what do you find T? What do you find as capital T? That is 1 minus capital R. So it is N1 square plus N1 plus N2 whole square minus N1 square plus N2 square minus 2 N1 N2 by N1 plus N2 whole square, right? So from here, when you take this term, this should be 4 N1 N2 by N1 plus N2 whole square, right? So the transmission coefficient capital T, which is your ratio of transmitted intensities, and that's what is asked in the question, that is given as 4 N1 N2 by N1 plus N2 whole square. So now for this case, it's 4 into 1 into 2 by 2 plus 1 whole square, right? So what you get? You get 8 by 9. Is it making sense? But you also feel the relation. Yeah, this I don't feel it as correct. Like I don't know how, like what might be the context in which this came up, but I have not seen transmission coefficient expression as just N1 by N2. So this rest of it is like clear, right? How you uh, the expression for transmission coefficient is 4 into N1 N2 by N1 plus N2 whole square. Not this relation, right? 2 eta by eta plus eta 1, not that. 4 eta 1 eta 2 by eta 1 plus eta 2 whole square. So that's your transmission coefficient. The 11th assignment problem. Oh, N1 is less than N2. Won't the light be focused in N2 instead of N1 so I need to know the question, what exactly the question is. Is it about the core and the cladding? N1 is less than N2. Won't the light be focused in N2 region instead of N1? If this question is about the core and the cladding, then there always the optical density of the core is greater than that of the cladding. So N2 is always greater than N1, because only then your total internal reflection will be possible. Okay. A symmetric dielectric slab waveguide is to guide light at some wavelength. The slab thickness is atho and the refractive index of the surrounding material. Okay. Determine the maximum allowable refractive index of the slab material that will allow single TE and TM mode operation. Okay. So, okay, one by one. Okay. Wait. This is something which we had discussed in the last class. So, one second, let me try to share. I think then it will be clearer. One second, wait. See here, what it is telling you is that, one second. So first of all, this is what it is telling you, that your N2 should be always optically rarer than N1. Only then your total internal reflection can happen, right? Because you remember rays always move away from the normal in the rarer medium. So if you want your light or your signal to be concentrated inside this region, in that case, your cladding or your N2 should be always smaller or lower than N1. So that is one thing. Now, the question that you asked is based on this relation. So it's based on this relation, right? So for a single mode waveguide, so if you look at this expression here, you would see that there is a self-consistency condition that always has to be satisfied. Okay, so which tells us that if your wave is propagating from, this is how your wave is propagating, then after two reflections, the wave that you get here is the same as the wave that you had started with at this point. So for that self-consistency condition, if you solve it, you would get an expression like this. Okay, and so this comes again from the Fresnel equations, which tells us how the phase change happens when there is a reflection at the boundaries. So if you add this phase change that happens because of the reflection and this phase change that comes because of the path difference, it has traveled some path, right? So the total phase difference should be a integral multiple of 2 pi m. Okay, and from there, if you put the expressions, you would get this kind of a transcendental equation, which, so this is the self consistency condition. Okay, so this tells us that for some values of theta, you would get some solution, right? So those will be your valid values of theta. Okay, so and that in a way would define or for some value of theta, there'll be some particular values of m which would satisfy these conditions, right? So that will define how many modes you can get, right? And you can see this, each of these gaps are given as lambda by 2d. So now what happens when this first point of intersection comes after the lambda by 2d? in that case, what you get is a single mode waveguide. Okay. So for single mode waveguide, your 2D by lambda naught is your wavelength in free space. Okay. So 2D by lambda naught into NA could be less than 1. And what is NA? NA is your numerical aperture. It is related to the difference in the refractive index of the core and the cladding, or the two mediums. Okay. Excuse me. Okay. So now if you use this relation, you can use this relation, putting like here, even here, these are all same relations. In this case, for a single mode waveguide, that means it supports only one mode. So in that case, M is just 1. So putting M equal to 1 in this expression and writing the numerical aperture by using this formula, you can try to solve this question that you just discussed. Right? Your lambda is given, your D is given, you know N2, you know N1 because it comes from, I think, free space to this medium, or maybe the two mediums are also provided. So all the values are given. So you have to find, you have to find N1, right? You have to find N1 where N2 is already given. So just try to use this relation. And if you use this relation, you have to find N1. All other terms are known. Your capital M is 1 because it supports only one mode. Okay.
Yes, madam. When we consider M equal to 1, it supports single mode, no doubt. But if we compare the N1 and N2, N1 is now less than N2 in this case. N1 goes to 1.431 and N2 is 1.45. This means that the light won't be confined to the N1 region. We can't get
Okay.
total internal reflection. That's the meaning.
So, no.
N1 goes less than N2.
Your N1 should be less than N2, right? In always the, see, think of total how does it happen? So it's like rays move in the rarer medium. This is a rarer medium, right? N1 is your cladding.
N1 is the denser medium.
No, I think the question, what it is saying is the slab thickness. Okay, so you mean the slab is surrounding material is N2. Oh, this is opposite, is it? Okay, then the question
if
is
you
opposite.
want the light is to be confined to N1 region, N1
Right.
must be greater than N2. This is
Greater
the
than
simple
N2.
comparison.
Correct. Yes, exactly. No, then
Now
there's
the result comes like N1 is 1.431 and N2 is 1.45, which means that the light won't be confined to the center core region.
right. Always the core should have greater N2, like greater refractive index than N1. Only then the this waveguide, like it can guide the wave to that path. Otherwise, it would all get. Yeah, that is always true. I don't know what happened to this question.
Yeah,
This
that's why
question.
while solving the problem, we took M equal to 2.405. That's the critical value we'll be using in optical communication.
Actually, see, these questions, so I neither do I make the questions, not do I correct it. Okay. So the main point is like your instructor, whoever has made this question, and they'll only do all this evaluation and everything. For my case, yeah. So for my part, what I was supposed to do is to just discuss the concepts and try to help you out in some cases if you are stuck. So I actually don't know why, like what might have gone wrong in this question, but
Okay.
in yeah, but in more like always this is the case that the core has a greater density than the cladding. So
Yes.
yeah.
The only answer that is above the 1.45 value is 2 in that option. We have 4
Oh,
options.
okay.
So 2 is
Okay.
given, so naturally we choose 2. That's how we did mistake, but answer is given as 1.431 as per the procedure you have explained now. M has been
Yeah, right.
considered as 1.
So yeah, because that's how it is to be done. But now I don't know how the values got, like, something might be wrong with the values. I don't know because I did not set the question. So like I'm also seeing the question for the first time here. So I don't see the assignment questions per
Okay, ma'am.
se. I
No
Yeah,
issues.
yeah. Yes. Um yes, I think NS you were also writing something and then I had to okay. The previous question, the transmission coefficients is 2n2 by n1 plus n2 that multiplied by 2n1 n1 plus n2 would become 4n1 n2 by n1 plus n2 whole square, which is the expression you stated. Yes. Yes. So, see, how you are defining your transmission coefficient makes all the difference. Okay, so if you write the transmission coefficient as just the ratio of amplitudes, then it is a different expression. If when you are talking about power, then you have to write it in terms of intensity. See, just by writing it as 2 n1 by n1 plus n2, even if you see, like, if you look at the expression for the reflection coefficient square, they don't match, right? So i- if you are talking about the power transmitted or power reflected, you have to take the square of ratio of amplitudes. Okay. Yes. So initially the mistake that we got stuck into was the fact that you were using it as 2n2 by n1 plus n2 as your transmission coefficient expression. But here when you are talking about power transmitted, you have to use the relation which comes from, either you can do it as, directly finding the ratios of amplitude and taking a square of it, or you can find the deflection coefficient for the amplitude, take a square that gives the reflection intensity ratios, and subtract it from 1. Okay, so that's how you get your transmission coefficient, capital T. So I think there was the confusion. So yeah. Expression for transmittance transmission coefficient. Okay. Um, okay. But now you understand, right? The correct the expression for transmission coefficient when you talk about power transmittance or intensity transmittance, and that's the general definition, is given as 4 n1 n2 or 4 eta 1 eta 2 by eta 1 plus eta 2. But that eta 1 by eta 2, just that, I don't know how that relation is coming. Yeah. Okay. Any further doubts? What advice would you give to get a strong grasp on electromagnetics? Yeah, particularly, so out of my, see, I'm also not very experienced, but out of whatever I have studied, I would say that, just it's about mainly thinking about what you have read. So try to focus on one textbook. Okay, don't it's important that you read a textbook properly. Just solving multiple questions would not be sufficient and you might miss on the concepts. So as per my experience, it's very important to focus on a standard textbook. So suppose for the normal the standard electromagnetism, you can follow Griffiths, and Griffiths is a very standard book which I followed and I follow. And for stuff like waveguides and all of this, so I think Saleh and Take is a very nice book. So try to follow some textbooks that would give you the concepts, and then you can look for questions. So for questions, there are multiple places. So these days, like physics and I don't know, I don't remember the names, but so you can find different question papers and like NET or JAM, JEST, and all this kind of question papers, which can have very standard questions. So you can try to solve them. That will keep you up to date with the concepts. But before that, it's very important. Please follow a textbook, like a proper textbook, because just remembering formulas and trying to solve them, you will, when you have multiple subjects coming in, you might miss on the concepts. So it's very important. Not too many books, but at least one or two good textbook. Yeah, thank you. Can you repeat the name for the waveguide text? Okay. Uh, One second. Thank you. Okay, yeah. Thank you so much. It feels great. Thank you. Yeah, thank you. Thank you. All the best for all your upcoming exams and endeavors. So, yeah, thank you. Thank you, Meenakshi.